Welcome. In this video, I'm going to talk about the equilibrium constant, or Kc. It's also referred to as K sub EQ, but IB tends to refer to it as Kc, so that's what we'll refer to it in this video. So every reaction has its own unique Kc value, and it's a fixed value or a constant for a specific temperature. This means the only thing that can actually change the equilibrium constant is its temperature. Now, in the next video, I'm going to talk about changing the equilibrium position, but that doesn't change the equilibrium constant. So, how is the equilibrium constant calculated? Well, remember, at equilibrium, the very definition is that your forward and reverse reactions are equal, so the concentration of your products and reactants is remaining consistent. So, when scientists did some looking at this experimentally, what they came up with is that the concentration of each product or reactant taken to an exponent equal to the coefficient of that reaction would yield this constant, or the equilibrium constant. So for the reaction, little a times capital A plus small b times capital B yields little c capital C plus little d capital D. You can see the equilibrium constant would be the concentration of C to the C value times the concentration of D to the D value divided by the reactants multiplied by each other in the same way. Now I've got EQM next to each concentration value, and that simply refers to the equilibrium mixture. So the concentration for each of those components in the equilibrium mixture. But usually we drop the EQM symbol off because it's kind of a given that the equilibrium constant would only apply when you have an equilibrium mixture. So second thing to mention is units. Some books, some professors derive units based on, you actually take your moles per liter per second and you square it or cube it or whatever is done to your concentration for each product and reactant, and you come up with a unit. So you can have weird units like mole squared, per liter squared, per second squared. But most people now actually just drop the units altogether because equilibrium is really seen as an indication of activity. So you really don't need units. What we're really looking at is how much greater or less than 1 is it, which is favored, products or reactants, and how significantly are they favored. The other thing to mention is that these are only concentrations of gases on the reactant and product side of the equation, because solids and liquids have a constant concentration known as their density, and that density is known for the temperature you're working at. So since those are constant values, they get rolled in with the equilibrium constant. So it's really only concentration of gas reactants and gas products being used to calculate the equilibrium constant. So again, because it's indicating activity, we really don't need units. We just need to know, is it more than 1 in favoring the products or less than 1 in favoring the reactants? And on this little chart below, what you can see is that once you get beyond 1,000, we're talking about an equilibrium getting fairly high and lying fairly far to the right. And when you get less than 1,000th, then Kc's getting very small and considered to lie fairly far to the left or in favor of the reactants. And they can exceed 1/1000th and 1,000 quite a bit, but those are kind of the rough markers of where we're saying it's really far to the right or really far to the left. Remember, the magnitude of Kc doesn't tell you anything about the reaction rate. It can reach this equilibrium very quickly or very slowly. And we are going to tend to be looking for, or in industry, you're looking for high Kc's because you're usually right in the reaction with the forward reaction being the desired reaction. There's also something called the reactant quotient. What would happen if you plugged concentrations into the equilibrium constant expression, but you didn't have concentrations at equilibrium? Well, you would still get a number, but it wouldn't be equal to your equilibrium constant. So instead, that's called the reactant quotient. If you look at your current concentrations of product and reactant, even though you know you're not at equilibrium, but you go ahead and plug them into the equilibrium constant expression, then you get this number, this reactant quotient, and it can tell you how far away you are from the equilibrium constant. For example, if you calculate it and your reactant quotient, or Q, is less than Kc, then the reaction needs to continue further to the right and produce more product. But if Q is already greater than Kc, then you know the reaction is going to proceed to the left in favor of the reactants. And if Q is equal to Kc, then of course you're at equilibrium. So here's an example of using the reactant quotient. Kc is known to be 170 at 500 Kelvin for this reaction. Determine what direction the reaction mixture will proceed, or if it's at equilibrium when the components have the following concentrations. So the first thing I need to know is what's my equilibrium constant expression. Well, by looking at this equation, I see that Kc should be equal to concentration of NH3 squared over the concentration of H2 cubed times N2. Sorry if I messed you up by reversing those, but that's just the direction I saw. And so then I can go ahead and plug my values in. So if I scroll this up a little bit, that means I can take 8.00 squared and divide by H2 1.00 to the third times 1.50. And I end up with the value of 42.7. So what does that tell me? Well, it tells me that 42.7 is less than the 170 it should be. So I need more product to bring that value up to 170. So my reaction is still moving to the right. How about if you change the reaction? What if you write the reverse reaction? What does that do to your Kc value? Well, as you'd kind of expect, if you write the reverse reaction, then your equilibrium expression is going to be flipped. The reactants are now the products are now the reactant. So you could expect that your Kc value should just be 1 over Kc for the forward reaction. So if you already know Kc for the forward reaction, you don't have to plug in concentration values. You can just take the inverse of it, and that should be Kc for the reverse reaction. And then a reaction can also be multiplied, or be multiples, such as double or triple. That also has a greater effect than just doubling or tripling. It does have effect on the Kc. So since a coefficient becomes an exponent, if you double a reaction, then you should square Kc. If you triple the reaction, you would triple Kc. While you half a reaction, you would take the square root of Kc. So an example of this as well. Again, if Kc is 170 at 500 K, what could we expect Kc to be if we flip the equation and cut the amounts in half? Well, flipping the equation, I would expect my Kc value to be equal to, my new Kc value to be equal to 1 over the original Kc. And the effect of cutting it in half means I should expect to take the square root of that. So I now need to take 1 divided by the square root of 170. And I'm getting a value of 0.077.